problem of applauding at the start is I will be worried at the end of my presentation, if you don't like it, then I'm not sure whether you applaud enough or not. So I reserve all the energy towards the end of the presentation. Thank you very much for coming. I appreciate coming on a Friday evening. I don't know how it works here in Italy, but in Silicon Valley, I live in Silicon Valley. People don't work on Friday evenings. And I'm so surprised to see some of the people are standing in the back. There's one chair there, I think, empty. If you guys want to stand, I'll sit there. I'll be speaking in English. Now, my wife tells me all the time, speak slowly. I tend to forget that, and that's the reason why she tells me all the time. I will try to speak slowly, and if you feel you have a question, or if you're not able to understand what I'm talking, please ask me the question. I'll talk about 3D point clouds, especially the deep learning aspect of it. In the next 45 minutes, I'll talk about some of the research that's been going on. Even though I will not be able to tell exactly what's happening in my company using point clouds, I'll talk about the research that's going on today. And because artificial intelligence, machine learning, deep learning, all of these topics are really taking off only in the last 4 or 5 years, even though the science part of it has been existing for the last 40, 50 years. The last 4 or 5 years have been really worthwhile for AI scientists. But as a point cloud or an image processing person or an AI scientist in image processing, I can see the dramatic changes that happened in the last 4 or 5 years, but more interestingly in the last 2 years. I'll try to talk about that today. 45 minutes is a short time to communicate what I want to. And I remember a long time ago, a person told me, if you want to understand 100% of what I spoke, you got to listen to my presentation 7 times. So today is the first time there's going to be a recording, and they're going to post the recording. Please watch it 6 more times. No, I'm joking. I will try to be as lucid as possible to talk about point clouds. Image processing, per se, has taken off a lot in the last 4 or 5 years. 2012 was the first time CNN-based image processing models were introduced. And before I get into the image processing history, point clouds are becoming really, really interesting of late because the sensors are becoming cheaper and cheaper. I think 3 or 4 years ago, LiDARs used to cost around 20, 25K or even 50K. But now they cost maybe, I think, 5 or 10K. But I think in a couple of years from now, they will be even as cheap as maybe $1,000 or $2,000. I am waiting for the day when you'll have a LiDAR sensor on your smartphone, so that you can take actually a 3D image of anything you see, wherever you go. But 3D sensors, 3D point clouds are being collected by industries to use in autonomous cars or autonomous vehicles actually, because you can use it in drones and also in any other flying objects. Also in augmented reality and virtual reality for gaming and other scenarios. But the also interesting aspect is the healthcare industry, especially for CT scans. You want to get a 3D image, not just a 2D image. Also, fundamentally we see 3Ds, right? When we look at an object, it's always 3D. It's not 2D anymore. And the object is going to be richer, the material and the information it has in the image is going to be richer, and hence you want to get 3D images and process it to find out what's happening in the images. So let's see. 2012 was the first image processing model that was published, which was using CNNs, convolutional neural networks. And 2015, the accuracy rate of models went up so much, the top 5 error rate of a CNN-based image processing model came down to 3.6%. What does it mean? If you give 100 random images to a model, it will make mistakes in only 4 images. 96 images it can very, very accurately predict whether it's a car or a cat or a dog or whatever. Even if the image is occluded, means it's partially visible, if the lighting is not bright enough, or the picture is blurry, it's too much noisy picture, you can still find out. Do you know what's the human performance? Human performance is around 5 to 6%. So, if you give the same images to human being, they tend to make mistakes in 5 or 6 images. So next time, if you have any of your naughty images, don't send them on the internet, because a model can figure out what's in the image. Whenever I tell that, people actually laugh. You guys ever think, you know, I'm an Indian guy, and I get more motivation when you smile when once in a while you show a facial expression. Okay, then I know I'm actually able to communicate to you guys. Yeah, is that okay? Yeah. Yes, yeah. And also for India, yes is this and no is this. In 2016, even though the information is not here, 2016, the top 5 error rate came down to 3%, and 2017, it's 2.6%. Models are becoming extremely precise, extremely accurate, extremely intelligent to figure out what's in an image. Imagine this use cases like a smart city solutions. You have a surveillance camera in a, let's say, a city like Milan. Even if you think of 10,000 cameras, which is actually small in number, every hour, how many hours of video is uploaded? 10,000 hours of video every hour in a smart city solution. You've got to have extremely intelligent image processing models to process to find out what's happening. If there is a crime that's going on. Do you guys watch YouTube? Yeah. You know how much of YouTube video is being uploaded per second? No. 300 to 500 hours of video is being uploaded every second. So next time you open a YouTube app, it picks up some of the videos it thinks are going to be interesting for you. So YouTube actually has a recommendation engine which is running in the background. It has already profiled you, it knows what you like, and picks up the appropriate videos for you in less than 30 to 40 milliseconds. And especially, so the recommendation engine actually has 2 models running simultaneously. One is it actually picks up around 500 candidate videos, and then you have another model which does the ranking part. Because even if you have 100 videos which are of importance for you, you really want to, the model wants to really show you the top 1 or 2. Because if you are watching it on a small mobile phone with a small real estate, you will not even scroll down if the top 1 or 2 or 3 are not of interest for you. So the pressure the image processing models, if they happen to be human beings, the amount of pressure these models have to really perform that fast. Now comes the scenario where you don't have the cloud computing, but you want these models to work on a mobile device, and that becomes even more difficult. I remember reading a paper published by Israeli University 6 months ago. It looks at the face of a human being, and it can actually make pixel-wise changes to convert the face. Let's say if it's a straight, non-smiling face, it knows what pixels to change to make it look like a smiling picture. So very soon, my prediction is, Facebook will introduce a new model. When you log into your Facebook account, your picture is there, the DP picture is there, but if your girlfriend or boyfriend logs in, the picture winks. When your mother or father or a kid logs in, the picture smiles at them. It's the same picture. And the model has to figure out which pixels, whether it's the pixels here, and the pixels here, all need to be modified to make a regular, ordinary looking photo to a smiling photo, or a frowning photo, or a naughty looking photo. So image processing is really becoming extremely interesting, more than natural language processing, more than predictive analytics, even though I come from an industry, a company which actually is focusing on Industry 4.0 solutions, all the digitalization of companies, or digital twins. Have you heard of the term digital twin? If you have, let's say, a car, I live in the United States, and I have an electric car. One day I was driving in the morning to work, and then I got a call from the dealer. It said, "Sir, your car has a air conditioning problem." I said, "What air conditioning problem? I just drove the car even yesterday. I was using air conditioning. Right now I'm not using it, but how do you know?" And I pressed the button, air conditioning button. It didn't work. It was working the previous day. The car company knew already that my AC is not working, even though I am the one who's actually managing the car. So predictive analytics and natural language processing, even though that's really progressing a lot, image processing in AI is really taking off. But these are all 2D image processing. But as I mentioned earlier, the real images are 3D images, and we're going to talk about those. 3D images can be represented in many ways. In the Euclidean data space and the so-called non-Euclidean data space. How many of you are mathematicians or computer science? Okay? Thank you. Euclidean data space has the unique feature where you can measure one point from the other point using some distance metric. And non-Euclidean, it's not that easy to measure. Let's just stick with that very, very abstract level definition. In the Euclidean data structure, you have the descriptors for 3D data points. You have projections, you have RGBD, volumetric, and multiview. I'll explain these. Descriptors are handcrafted descriptions of the objects. People don't use it for deep learning anymore. So let's not talk about that. Projections. A couple of years ago, when image processing models were being talked about, people thought, can we use a 3D image, project it onto a 2D space, and then run the regular CNNs? Why? Because CNN-based image processing, 2D image processing models are really intelligent. They're very stable. The previous slide actually showed that. The accuracy, the top 5 error rates are really, really low. So the idea was to project a 3D image into a 2D space and do the processing. It worked for a while, but not really at high accuracy. RGBD is using the regular RGB colors and also the depth dimension of a point of a 3D information could be used. It's called 2.5 dimensions because RGB is in 2-dimensional and depth is, we call it as half dimension. It has to be exciting, right? Sometimes mathematicians are really boring people. How do you know it's boring people? I know many of you are mathematicians, sorry for that. I'll tell you the reason why they're boring people. And computer science people too. You know, in 2016, October, a unique technique of image processing called RCNN was introduced. It's called region CNN was proposed, which actually can do the localization. That is, if you have a picture of multiple cats and dogs, the model will draw a bounding box of where the cats are and the dogs are and then do the classification. After 4 months, a new model, an upgraded version of it was suggested, and it was named Fast RCNN. 6 months later, someone came out with even a better technique, and it was named as Faster RCNN. Only engineers can do such naming conventions. The marketing and sales and other people can do a really intelligent and sexy terms, but
like
that's
more faster.
Yeah, the more faster, and very, very faster. And even this one came out, I think, 6 months ago. It's called Mask RCNN, which is slightly different, but it's better than Faster RCNN. The name is slightly different. Anyway, RGBD is 2.5 dimensions. Volumetric representation of 3D images is, if you take an image, let me use the water cup. If you take a 3D image of this cup, this is empty inside. But for processing, you convert this image into something called voxels. So you voxelize the image. So what you're doing is you just fill up the whole thing and tell the image processing model, this is just only the surface outside. Everything is inside is just full. Even though you don't actually have anything there, you're actually confusing the model of the depth perception. You're just thinking it's completely full. That's called voxelization. Some of the models actually work decently well, but that's not the reality again. You're actually transforming a good image into a bad image and asking the model to figure out what's happening. So it doesn't work that way. There was another technique called octree. I'll show you a couple of models proposed based on that. Octree is a data structure where you recursively break down the image into pieces of 8. And you keep on doing it till the pieces become small enough for you to process it. So you have a node, you have 8 subnodes, each of the subnodes will have 8 more subnodes and keep on doing. So you break it down and then you look at individual pieces as a 2-dimensional image and then process it. And I'll explain that more. Another suggestion that was made some time ago, if you have a 3D representation of data, like for example this same image, they said instead of taking a 3D image, can you take a 2D image from multiple locations? It's called multi-view 3D representation. So you're actually translating or transforming a 3D image into multiple 2-dimensional image. Again, the reason being, if it's a 2-dimensional image, you can use the regular CNNs. You know, that reminded me of this English proverb. If the only tool you have in your hands is a hammer, every problem looks like a nail. So everyone, all engineers were converting the 3D into 2D because the only tool they had was CNN. Even today, it's still CNN itself we have as a solution. And I'll talk about some variations of CNNs being used, and instead of using a 2-dimensional way CNNs, we can use about something else too. The non-Euclidean data representations of 3-dimensional images could be point clouds, graphs, and meshes. You know, as an AI scientist, we don't agree with each other. We all think we are so intelligent. We just don't believe the other guy is intelligent or the other guy is intelligent. So there is a debate going on whether point clouds actually will fall into an Euclidean space or a non-Euclidean space. This image I picked up from some paper, even though I don't believe it's a non-Euclidean, I think it's an Euclidean image, but I grudgingly put it there. I said, okay, let's leave it there because I'm sure someone is going to comment on it. Because I don't know if you're recording it, I have a YouTube channel and I put my videos on YouTube, and I'm sure people are going to comment on that. They watch and say, hey, you're wrong, and people like, you know, people like telling the other person you're wrong, especially in the AI world. So anyway, point clouds are becoming really popular of late because of the sensors becoming more and more cheaper. LiDARs, for example, and there will be more and more point clouds coming in. Graphs and meshes. Graphs, I think, is more of the regular graph structure where you can organize a 3D image using graphs. But I've shown a couple of models in my presentation, but not really popular. Meshes is nothing else but you have a bunch of polygons, let's say triangles. All of these triangles are connected with each other. So the vertices of every triangle connects or touches the vertex of another triangle, and hence you have a bunch of triangles which will cover the 3D image, and then you can run a CNN model of that. Why? Point clouds are irregular and unorganized. Have you ever seen a point cloud? It's like if you look at this room, you see the ceiling, you see a couple of lamps hanging, you see lots of chairs here, and then maybe the walls with the window, the glass panes. If you run a LiDAR to take an image of this, imagine all of these are shown in that as just only dots. And the dots sometimes are dense enough, sometimes they are not dense. For example, if I put a LiDAR here and if I take an image, this wall, this edge is so precise because every maybe millimeter there's a dot and you can see a very clear wall. But if something is not illuminated enough, or if the object is moving, the density varies. It just, the model misses some of the LiDAR misses some of the points. Point clouds are irregular because you just don't know where you'll find a point. It's not like a 2D image. If you take a 2D image, every pixel has a value. The RGB values are encoded in every pixel, and you will know there is a pixel every place on the image, because if it's a background or the image, there's a pixel there. But I think in a point cloud, sometimes there's an empty space, there's no point there. But of all the 3D representations, especially point clouds are canonical. What does it mean? the advantage of a point cloud is you can convert a point cloud into any other 3D representation, and you can convert any 3D representations into into point clouds. That's the advantage of it. This is a quick summary, but you don't need to pay too much attention to this. For every type of data representations, there are models available for traditionally the descriptors or projections, or even RGB type of images. The temptation is to use CNNs to process the image and figure out. And typically when I say image processing, it could be classification, localization and detection, and sometimes semantic segmentation. The most number of use cases in the world today for 3D processing are in semantic segmentation. And I'll tell you, do you know what a semantic segmentation is? Yes? Yes? This? Yes? No? Okay. Let me explain. Let's say I have a couple of cups in my hand, even though it's only one cup, I imagine there are 2-3 cups. When you do a semantic segmentation on that image, the model will find out there are 3 cups, and each of the cup will be colored different. So every pixel or every point will be colored in different. So all the pixel that belongs to, or all the points that belong to this 3D image, and this 3D image, and this 3D image will be of different color, and all the points that belong to the background will be colored entirely different. So in other words, when you do a classification where the entire object is classified for certain class, in semantic segmentation, you are actually classifying every point. In other words, if you have 200 million points in one point cloud, we have LiDARs in my company, and the most recent one, which we recently released in the Las Vegas convention in June of this year, is called BLK360. It takes, we use it normally for factories and industries. Normally the number of details in a factory is a lot more. You'll find lots and lots of pipes and pumps and turbines and so many different things in a factory, and then the finer details are too many. If you take one image of the factory using a BLK360, which is LiDAR, it takes less than 2 minutes. It takes, the image is of the size half a terabyte, anywhere from 200 to 300 million points. In less than 2 minutes, it takes an image. But imagine now you're having that LiDAR on your autonomous car. Whatever car you drive, and I know the speed limit in this country is 130 kilometers, but I never see that cars are going faster than that. I am driving at 129, and I'm watching all the cars going, crossing me. And maybe one of you guys tell me after the presentation today, what is the real speed limit? Because I was trying to. But anyway, let's talk about it. If that LiDAR is sitting on your car, and if you want to drive at the speed of 130 kilometers per hour, you want the model to be extremely fast to figure out, is there a car in front of me, or a pedestrian in front of me, or a tree in front of me? And then, of course, after that, you still have to do some decision making, which, even though, let's say, that if that's instantaneous, but the model has to be so fast to do processing of it. Okay, let's go to the next one. I'm going to show a few of the published reports. I think I have 9 to 10 papers. Every paper, I put the link at the bottom. One reason of putting the link at the bottom is, of course, to let you guys take pictures and go back and read more. But another thing is, see, sometimes the topic gets boring, and if you are sitting relaxed and the air conditioner is working fine, and then Friday evening, I can imagine maybe you'll start thinking, okay, after this I'm going to go to a pub and have a drink. And just to break that thought process, you can take out your phones and take a picture of the screen. That is another reason why I put the link at the bottom. And I can give the slides to you guys later on, but right now I will say I'm not going to give you so that you can take pictures. But I'm going to give you.
I'm using fast CNN.
Yeah, fast CNN you can. So OCNN and next model is OCNN, but let me first talk about this. The entire technique in this paper is very, very simple. Using octree data structure, which I described earlier. Octree is nothing but a data structure that recursively breaks down the object into 8 pieces and further to 8 pieces. Here you take an object and break it down using octree data structure to a certain level. So you have an image, if you have an object, like for example with an airplane, you break down that into 8 pieces, further 8 more pieces, more 8 pieces, and each of that piece, whenever you stop, becomes your receptive field. And you stack up all of those things one on top of the other. Now, what is the next step? Just use the regular CNNs. If you have, I don't know how many of you have studied the image processing using 2D CNNs. If you have RGB values, so right there you have 3 channels, red, green, blue, of the pixel values. So you have 3 receptive fields, and then you run a kernel on top of these receptive fields. A kernel is nothing else but a matrix with random numbers in it. The matrix could be of a size 2 by 2, 3 by 3, sometimes 7 by 7 or 5 by 5 too. But the most common kernel size of nowadays is 1 by 1 or 3 by 3. You can just take it as a standard. You can do other things too, but the most effective ones. That's a standard 2D image processing, and all that the paper is trying to do is, how do I convert a 3D representation into 2D and then use a regular CNN? So this paper and the next paper, if you want details, you should read the paper. This and the other paper both are using the octnet or octree data structure and a bunch of pooling layers, and the model does the classification and semantic segmentation. 10 more minutes? Okay, so let's talk about this one. You know, one of the things my professor used to do a long time ago, of course he was messing with us. He said, okay, I'm going to ask questions on this slide I'm going to present to you guys today, and then we will frantically making notes, but he doesn't ask questions, but he just only makes you actively listen to the professor. So I'm going to do the same trick on you guys. I'm going to ask you questions on this slide. Okay, pay attention. PointNet is the first model which has become extremely popular of all other models in point cloud processing. So they call it as PointNet. This is the first model which takes point clouds or the raw point clouds in the raw format without any pre-processing. Till then, all models had to pre-process the data set, maybe convert it into a different format, different 3D representation to process it, but the PointNet is the first one. And here too, it's very, very simple technique again. They take every point out. So every point has a dimension x, y, z, right? Because now we're talking about 3-dimensional image. You can also add additional dimensions if you want. For example, the brightness of the point, or the color, the RGB colors too, if you want to. But let's say you have a grayscale point cloud image, and you take the XYZ coordinate alone per point. So a point is defined by XYZ coordinates. And because point clouds are invariant to rotation, what does it mean? If you have an image like this, and if this is a cup, when you turn it, it's still a cup. If you turn it, it's still a cup. Take an image of this room with the lamps, the chairs, the walls. When you turn it, it's still the same image. It's invariant to rotation. So the relative position of the points, they are locally important, but globally it's not that important. So what they propose in this is, take every point, if you have 1 million points or 200 million points, arrange them in a sequence of table, x1, y1, z1, x2, y2, z2, x3, y3, z3, keep on doing it. And then you do a little bit of a transformation. There is a transformation, 2 types of transformations. I will not explain this, but in very, very simple terms, it's just running 1 by 1 and 3 by 3 convolutions on it just to get the receptive field out of it. So you do a transformation. Otherwise, you put the data set through MLP, multi-layer perceptron, almost like an RNN. You have a bunch of activation fields, bunch of redos, and bunch of batch normalizations. That's it. So the most basic neural network approach is used, and you run the whole model, the whole point cloud, and you do a max pooling. Why max pooling? They said a symmetric function will give the best results in point cloud. And what is a symmetric function? Again, is a mathematical. How many of you guys, you said there's one mathematician I said, but rest are all computer science engineers. Symmetric function is operation you do on a set of data. In any sequence, the answer remains the same. Like addition is a symmetric function. 2 plus 3 is same as 3 plus 2. Multiplication is a symmetric function too, right? So max pooling is a symmetric function. Average pooling is symmetric function. Weighted average pooling is a symmetric function. So they found between max pooling, average pooling, weighted average pooling, they found max pooling is giving better results. So all that they do is do a max pooling and convert the entire point cloud into a single global feature. And that global feature is used for scoring and then classification of the object. If the point cloud is about one object, you can do a classification of it immediately. If the point cloud has multiple objects in it, you can do a semantic segmentation. You add another layer, add the global feature that you bring out from the first network, and add that to every point in the point cloud. You concatenate the local feature, that is every point with the global feature of the entire image together, do the processing again through multi-layer perceptron, and you get a semantic segmentation. It's as simple as that. How many more minutes?
I mean,
5 minutes more? So,
7, by the way.
7, okay.
5.
I was planning to talk to you guys for a longer period. So it looks like I think Friday is going to be short for you. I think you're getting a chance.
It was 40 minutes.
Sorry?
It was 40 minutes.
Oh, I'm already done 40 minutes?
Yeah.
Okay.
Yeah.
Sorry. This paper, authors came out with another model called PointNet++. And the reason why they did this was, in the PointNet model, it was not paying attention to the local features. What does it mean? If you have, let's say, 10 chairs in an image of a point cloud image of a room, the model was not effectively picking up the legs of every chair, especially if 2 chairs are close to each other and both the legs are close. The model gets confused where the one leg of the one chair and the other leg of the other chair is. So the local features are not being paid attention to. So they said we are going to run PointNet recursively for every few points. So they pick a few points, in this case, one leg of a chair, maybe 2 legs of a chair, or just the back support of a chair. They would run a PointNet. Remember I said, every PointNet will give a global feature, but because they're running a PointNet on a small chair or just the leg of a chair, that's actually a local feature, not a global feature. And you run it recursively on all the points. So now the model knows every leg of the chair, every back support of the chair, and every chair in the image, and every human being in the image, every hand of the human being in the image. So now the model is becoming extremely precise and intelligent. Only thing is the computing cost is very high. That's about PointNet++. I do have information about so many other models. For example, SplatNet is an approach where instead of taking a square-shaped kernel, like a 2x2 or a 3x3 or even 1x1 kernel, which is used in a 2D model, they use a lattice-spaced. So what they do is they take the point clouds, put a lattice on top, there is a mesh on top, and you see some points fall in the middle, some points with the GPU going on, but there is soon a time where almost all the AI models should be running your mobile device, like your laptop, your iPad, and your smartphones. And then it's just not the GPU alone, but there's so many other things that need to be done to make the model run on a very small footprint and small power supply and a little bit of storage and all of that stuff.
Also in the training.
In the training, we do it on the cloud. We do it on the cloud all the time because majority of the time when you do a training of a model, they do it on the cloud. When you're inference time, I think it should be in any device model. GPUs, yes, I think it's like a commodity, but I don't have too many comments on that. I think it's just whatever is cheaper, I think we just go there.
Okay. Yeah, I just was going to ask, talking about image processing, and you look at megatrends with technology evolving so fast, digital transformation, industry 4.0, what would you say are the critical challenges that image processing is facing?
Awareness is a huge challenge for me. When I'm the chief product officer of the company and I talk to all the division presidents, many of them are, not many, all of them are intelligent. You're recording it, right?
Yeah.
Okay, no, all of you guys are intelligent.
All these
A really strong proof of concept. So I was curious to know, like, how important is learning, and how does learning tie in with AI and sort of the innovation around AI in Industry 4.0? How does it tie into the critical business needs or the technical needs for a company?
Okay. Yeah, maybe I think you should sign up for the deep learning workshop. I think he'll tell you what to do here. That's he recommended. I'm not saying you should or should not. The learning, if I understand your question correctly.
Learning as in like people learning as technology evolves to be sort of adapting to what is happening around.
I think it's a slam dunk. I think people should just learn new things. Especially AI seems to be so impactful on so many different things. See, have you heard of Netflix experiment? Almost, I think, 3 years ago, 4 years ago, maybe even earlier than that. They said they will give $1 million to a person or set of people who can improve the accuracy rates of their recommendation engines by 10%. And there was such a tremendous amount of participation. Every company, have you heard of the book called Crossing the Chasm? Crossing the Chasm. Yeah. If you have not read the book, you should read the book. By a guy by the name Jeffrey Moore. He talks about innovative companies would work on the technologies, and early adopters would adopt the technologies very, very fast, even the unproven technology. And they are the ones who get the early mover advantage, and they really prosper a lot. And you also have the late adopters and you have the laggards. But if companies don't learn, if your question is, I think, should they learn? People should learn. People have a different learning curve, companies have different learning curves. But companies really need to do the learning curve.
Yes, yeah, just a quick question. How do you see the rising of automated neural network design tools like Google ML impacting this evolution of the image processing?
See, 2 years ago there was no AutoML. Now I think there's a concept of AutoML. 2 years ago there was nothing called explainable machine learning. Now they have explainable machine learning. When I started working on TensorFlow, it was only 0.8 version. It is now, of course, 1.7 is available there. So some of the capsule network was not even there a year and a half ago. Now we have capsule network approach. Point cloud processing was not even there 2 years ago. Now we have one. I don't know what's going to happen in 2 years from now. Things will be dramatically different. If anyone says, I know what's going to happen in 2 years from now, go to Wikipedia and search for a person called Philip Tetlock, T-E-T-L-O-C-K. He's a professor in the United States. He did a research on when people make predictions, how good are these predictions? And you should read the book. The summary of it, the more intelligent, the more expert a person is in a topic, the less accurate their predictions are. So my predictions, having said that, my prediction is no one knows what's going to happen. Yeah, I don't know. I'm sure there'll be new techniques coming in.
Other questions?
Yes.
Yeah, before you were talking about cameras in the cities, and later you were talking about mobiles and this kind of thing. So in these kind of models and techniques, in the evaluation phase, how separated they can be, I explain myself. Can you just do one part of the computation on the cameras and then send some semi results to
yes.
a cloud?
The answer is yes, yes.
So this is taught for this.
Oh yeah. There are multiple types of solutions. For example, there's no processing sometimes. There's semi-processing, like you said, and sometimes there's a complete processing, and then the model decides, I don't need this data, and so it just throws the data away. There are multiple things to be done because you don't have the bandwidth just to store or even transmit on the networks too. Sometimes you just don't need the information. Sometimes you want to, let's say if it's a traffic congestion you want to study, you want to take intermittent results and put it in some place for longer term study. Yeah, there are multiple situations. It's all use case based, whatever use case you're trying to solve.
Last question.
So it's a more technical question about capsule, of course. Capsules are really different type of neural networks for computer vision. It works with neurons, not with neurons, and with capsules that are a group of neurons. And the main difference is that we can storage our features and we can preserve the hierarchy of data. So it works with convolutional, but it works in not in two-dimensional space, and works also like autoencoder because they can segment the image. So if you can spend just a few words, because I'm really interested about this topic, because when I said capsules, the main problem was that the features and hierarchy of data are allocated in a tensor, in a capsule, a dimensional, but it isn't optimized first, and the second point is that there isn't a structure how these features are located and how can generalize of viewpoint invariant. So I'm trying to understand if maybe work with mesh or manifolds and integrating these two words can be the next step, or maybe capsule is beautiful for research and not so beautiful. So your question.
That's a long question.
Yeah, I know.
I have a long answer too, but I don't think you'll allow.
What's the final project of this guy? So you know, 1 year to study this stuff.
Yeah, we don't have enough time, but capsule networks actually showed a tremendous amount of potential. They were introduced in October 2017 by Jeff Hinton. There were 2 papers published by he and his research associate. I think not enough research has really gone into it after that. It says there's not people I think are still publishing papers. I've seen very few papers, and maybe another 6 more months you'll find a lot more papers coming out. There's one dramatic feature capsule network showed compared to a regular CNNs is it actually has a hierarchical view of the components of an object. The famous example Jeff Hinton talks about why capsule networks are better than CNNs is if you give a face to the model and you have 2 eyes and 1 nose, 2 ears and a mouth, and the model says that's a human being. But let's say you move this eye here and move the lips here and move both the ears here, and you give it to the model will still think that it's a human being because the individual components are there and hence it's a face. But it's no more a face anymore. So the hierarchical view of the individual components of an object was missing. And that I think is really, really important, because if the model can figure that out fast, you don't need hundreds of thousands of images to train a model. Maybe I think a few dozens or maybe a few hundred in the worst case to train a model. But I'm waiting for the more research to be done by the company too. I personally am not doing the research on that area because in my company in Industry 4.0 we are doing research topics and so many different things. Anyway, I know we need to end, but here is one challenge for all of you guys. If you think you're really smart and you're really intelligent, and if you have a critical thinking mind, I have 3 or 4 use cases. I have a real complex problem and I don't know how to solve them. And it'll be nice if I can tell you the problem and then you can say, you know what, try this, and I'll be very delighted.
Using our blog.
There you go, please. So, if you want to send an email to me and my LinkedIn, I'm actually on LinkedIn. You can send me a connect, and if you're really curious and if you think you are a critical thinker, send me a connect and then send me an email and then I'll send you the problem statement and then you can talk. And I'll try to do a blog too. But anyway, thank you very much guys, I appreciate it.